Okay, so today what I'm going to go over is epoxides and ring opening of epoxides. So epoxides start with just a double bond and some kind of peroxy acid. So this is usually MCPBA, or you can actually see the peroxy acid drawn out. It looks like a carboxylic acid where they made a mistake and added too many oxygens, or sometimes it'll just say peracid or peroxy acid. So if you have that, then a peroxy acid with an alkene, an epoxide will form, and actually stereochemistry will be retained. So see how this is a trans bond? So the methyls are ones up and ones down. They'll maintain that as the epoxide is formed. So you have two different ways that you can open epoxide, especially if it's asymmetrical. So say we start out with this alkene, and we add a peroxy acid to it, and we get this epoxide. So with that epoxide, let me zoom in a little bit so you can see better. So with that epoxide, this can be it's like very strained. It's a small, you can see with the modeling kit, it's such a small triangle. It's always trying to basically just burst open wherever it can. So with that, anything that can attack it even a little bit is going to. So we can either attack on the more substituted or the least substituted side. And if you have a base catalyzed, it'll attack the least substituted side. And acid catalyzed, it'll attack the most substituted side. So I call that BLAM, base, least, acid, most. I got that from somebody at some point way back in grad school. So you can thank them. So base, least, acid, most. And I'm going to draw first the base catalyzed ring opening. So this is similar to an SN2 mechanism where if we have this epoxide and we're just going to make this the nucleophile. So if you have some kind of nucleophile like this, sorry, my lighting's just been a little weird today. That's a little bit better. If you have a nucleophile like this, it's going to, here's the most substituted side, here's the least substituted side. So the nucleophile is going to attack the least substituted side because it's negative, so it's more base catalyzed. And then this will open up because there's already 4 bonds to this hydrogen, or to this carbon. You have 2 implied hydrogens here. So a bond has to break. And because this bond is already polar, the oxygen is pulling some of the electron density towards it, it's easy for that bond to break out. So very similar to a leaving group leaving, even though this isn't a great leaving group, it's happy to do it because of all the ring strain that exists in epoxides. And I always number my carbons here because I'm very good at losing them. So carbon 1, 2, 3. So carbon 3 is where there's an attack. So the electrons from this oxygen fill in between carbon 3 and this oxygen to form a bond, and it brings its ethyl group with it. And then carbon 2 has 2 methyl groups on it. And this oxygen is actually still attached to carbon 2, right? Like this bond broke, but they're on the between 3 and the oxygen, but carbon 2 still has its bond. So you get this ring opening. The ring has been burst open by the attack of the nucleophile. And then if you want to make this an alcohol and make it more sturdy, you can add acid and you'll get an ether. So you just made an alcohol and an ether from an epoxide. Now, if you have acid catalyzed, it actually is going to be more similar to SN1. Now, it's not a full SN1 reaction because the leaving group doesn't fully leave because there's no rearrangement. We don't see any rearrangement, so we know this doesn't fully happen. But acid catalyzed ring opening of an epoxide, it has something like H plus and then like an alcohol in there. So this is the exact same starting epoxide, but the first step is actually that this alcohol is going to take this proton and protonate. So now this is a good leaving group, right? And similar to SN1, you could imagine this may be, because this is so strained, this ring may be leaving or breaking open on its own, and you getting something like this structure here where it's taken the electrons from this bond with it and the bond broke, and then it leaves behind a carbocation right there. So you can imagine that happening pretty easily, but we don't actually observe any rearrangement. So I don't think we know for sure. We don't think this step, as chemists, we don't think this step occurs. We think instead what happens is that departure is like starting to take place, and you get a really strong partially positive on this carbon right down here. Either way you think about it is fine, but if you do draw this mechanism out, you could get that answer wrong on your exam, because technically we don't think that this is how an epoxide ring opening takes place. But you can think of it in that it's similar to SN2, and that's why the nucleophile in this case, which is a weak nucleophile, attacks there, or you can draw it attacking here and then that breaking. I'm fine with you thinking of it either way, but you don't want to get it wrong on the exam. So depending on who your professor is, this isn't widely accepted as the acid catalyzed ring opening, but it's easier for me to think of it like an SN1. So you have the same starting material and a very similar nucleophile, but because there's protons hanging around, the first step is this gets protonated and you get attack on the more substituted carbon. So acid more substituted. And 1, 2, 3, 1, 2, 3. You get a bond between carbon 2 and the nucleophile that attacks. And actually, initially, this is still protonated because it's an alcohol that attacks, but it will get deprotonated in the final step. And so you end up with a structure like this. So I always do number my carbons because I lose them in ring opening of epoxides, especially if this is like more complex than just one triangle. It's easy to add or subtract carbons on accident. So I always know where the ring opens, but you can see how different. We started with something very similar. We had very similar nucleophiles, but one gives you this structure as a final answer, and one gives you this one. So one has alcohol on the original carbon 2, the other has the ether on the carbon 2 and the alcohol on carbon 3. So that is a quick overview of how ring openings of epoxides work. If you have any more questions on this, please feel free to let me know and I'll try to clarify them out. But really, if you remember BLAM and you remember it's similar to substitution reactions, you should be fine. And this carbocation, remember, doesn't actually form. It's just kind of a placeholder that I put in to help students see why it attacks more substituted as the acid. The base attacks the less substituted because it's less hindered, just like an SN2. So I hope that's helpful. Let me know if you have any questions, and happy studying.